This training is provided by SafeShield. We're a professional training provider that specializes in cybersecurity, compliance, risk management, and AI governance. Our goal is to give professionals the knowledge and skills required to advance their careers and get ahead of the competition. This free course is part of that goal. We want to make trusted, high-quality education accessible and to support the development of responsible practices in new and emerging fields such as AI governance. Fairness in artificial intelligence is not just a desirable quality. It is a fundamental requirement to ensure that AI systems serve people equitably and responsibly. When we talk about fairness, we refer to the absence of systematic bias, unequal treatment, or discrimination in the way AI makes decisions. This is especially critical because AI increasingly influences decisions in sensitive areas such as hiring, credit scoring, healthcare, policing, and education. A biased algorithm in any of these contexts can cause real harm to individuals and communities. The introduction of fairness as a design principle reminds us that AI must operate within the ethical and social expectations of the societies in which it is deployed. Fairness is also about legitimacy. Organizations that fail to demonstrate fairness face reputational, legal, and financial risks. Many international frameworks, including ISO 42001, the European Union Artificial Intelligence Act, and the NIST AI Risk Management Framework, emphasize fairness as a core principle. In this course, we will explore fairness not as an abstract concept, but as a practical requirement. We will discuss how unfairness arises, how to detect it, and how to implement safeguards to mitigate discriminatory outcomes. The goal is to equip you with both the conceptual understanding and the practical tools necessary to ensure AI systems are developed, deployed, and monitored with fairness as a guiding principle. Why does fairness in AI matter so much? The answer lies in the impact that AI has on human lives. Unlike traditional software, AI systems often make probabilistic predictions or recommendations based on large datasets. If those datasets reflect existing social inequalities, then the AI can unintentionally perpetuate or even amplify them. For example, if a hiring algorithm is trained mostly on resumes of men, it may learn to favor male candidates, disadvantaging equally qualified women. This creates systemic harm, undermining trust in AI and widening existing disparities. Beyond the ethical imperative, fairness is also a legal and regulatory concern. Anti-discrimination laws, data protection regulations like GDPR, and emerging AI regulations in Europe and other regions require organizations to actively prevent unfair outcomes. Fairness also has a business dimension. Customers, employees, and partners are increasingly demanding that companies adopt responsible AI practices. A lack of fairness can lead to customer distrust, regulatory penalties, or even lawsuits. On the other hand, fair and inclusive AI systems can strengthen brand reputation, increase adoption, and create new opportunities. Fairness matters because it ensures that AI does not replicate past injustices, but instead contributes to a more equitable society. This emphasizes that fairness is both a moral duty and a strategic necessity. To understand fairness, we must first define bias in AI systems. Bias in this context refers to systematic deviations in outcomes that unfairly disadvantage or favor certain individuals or groups. Bias can enter AI systems at different stages of the life cycle, from data collection to model training to deployment and monitoring. Data bias, for instance, occurs when training data is incomplete, unbalanced, or unrepresentative of the real population. Imagine a medical AI tool trained mostly on data from one ethnic group. It may perform poorly for others. Algorithmic bias arises when the model structure or optimization techniques inadvertently prioritize one group's outcomes over another. There is also human bias, which reflects the assumptions, values, and decisions of developers, data scientists, and managers who design and deploy AI systems. Not all bias is inherently bad. Bias is sometimes necessary for making distinctions, such as prioritizing urgent cases in healthcare. However, harmful bias is what we must detect and prevent situations where groups are treated differently without legitimate justification. Bias is not always easy to spot, as it may be hidden within complex datasets or algorithms. That is why organizations need robust mechanisms for bias identification, measurement, and mitigation. Here, we establish that bias is the root cause of unfairness, and managing it effectively is central to achieving non-discrimination in AI. Bias in AI can take many forms, and understanding them is critical to addressing fairness. One common type is historical bias, which occurs when datasets reflect existing inequalities or prejudices. For example, policing data may disproportionately include arrests of minority groups, leading the AI to associate crime with those communities. Another type is representation bias, where some groups are underrepresented in the training data. This is common in facial recognition systems that perform poorly on darker skin tones because the datasets used to train them were dominated by lighter-skinned individuals. Measurement bias arises when the way data is collected or labeled systematically disadvantages a group. For instance, standardized test scores might not fully capture intelligence, but if used as a training variable, they can perpetuate socioeconomic disparities. Aggregation bias happens when diverse groups are treated as if they were homogeneous. An example would be grouping different ethnicities into a single minority category, which hides critical differences. Finally, evaluation bias occurs when performance metrics favor one group over others, such as accuracy measures that mask higher error rates for minorities. Each type of bias introduces risk and requires different mitigation strategies. Recognizing these categories helps practitioners understand where to look for fairness issues and how to design interventions. This emphasizes that bias is not one-dimensional. It has multiple forms that must all be addressed to ensure non-discriminatory outcomes. Fairness in AI is grounded in both legal frameworks and ethical principles. Legally, many countries already have anti-discrimination laws that prohibit unequal treatment based on protected characteristics such as gender, race, age, religion, or disability. For instance, in the United States, laws like the Civil Rights Act and the Equal Credit Opportunity Act provide strong protections against bias in employment and lending. In the European Union, the Charter of Fundamental Rights ensures equality before the law and prohibits discrimination. The upcoming EU AI Act explicitly places fairness and non-discrimination as mandatory requirements for high-risk AI systems. Beyond law, international standards such as ISO 42001 and the NIST AI Risk Management Framework embed fairness as a guiding principle. Ethically, fairness aligns with broader human rights principles, including dignity, justice, and equality. Organizations deploying AI are expected to follow ethical codes of conduct that go beyond mere compliance. This includes respecting the diversity of users, preventing harm, and promoting inclusivity. Importantly, legal compliance does not always guarantee ethical adequacy. An AI system may technically comply with anti-discrimination laws while still creating outcomes that feel unfair or socially unacceptable. For this reason, organizations must consider both the letter of the law and the spirit of ethics in their AI strategies. This lays the foundation. Fairness is a legal obligation and an ethical imperative, and organizations must internalize both dimensions. Non-discrimination is a cornerstone of fairness in AI systems. It means that individuals or groups should not be treated differently based on irrelevant or unjustified characteristics such as race, gender, religion, disability, or socioeconomic background. In AI, this principle translates into ensuring that algorithmic decisions do not create or perpetuate inequitable outcomes. Non-discrimination requires a proactive stance. Organizations must not only avoid explicit bias, but also identify and mitigate indirect or unintended discriminatory effects. For example, a lending algorithm that considers postal codes may indirectly discriminate against certain neighborhoods if those areas historically correlate with lower credit access. Similarly, Using gender as a proxy for job performance is explicitly discriminatory. The principle of non-discrimination is embedded in many international frameworks. ISO/IEC 42001 requires organizations to adopt policies ensuring AI systems respect fairness and equality. The EU AI Act explicitly bans discriminatory practices in high-risk applications, such as employment and law enforcement. Non-discrimination is also consistent with the OECD AI principles, which call for inclusive growth and fairness in AI development. Ultimately, non-discrimination in AI is not only about avoiding legal violations, but about reinforcing trust, legitimacy, and social acceptance of AI technologies. This emphasizes that organizations must embed non-discrimination as a fundamental design principle throughout the AI lifecycle. Unfairness in AI does not emerge randomly. It has identifiable sources. The first is data quality and representativeness. If datasets fail to capture the diversity of the population, AI models will make decisions that favor some groups over others. A second source is design and modeling choices, where algorithms are optimized for efficiency or accuracy without considering fairness trade-offs. For example, a recruitment system might prioritize candidates with certain academic backgrounds, unintentionally sidelining equally qualified individuals from non-traditional paths. Another source is deployment context. Even if an AI system is trained fairly, when deployed in environments with structural inequalities, its outputs may still have discriminatory effects. Organizational culture also plays a role. If developers and managers lack diversity or awareness, bias may go unnoticed or unchallenged. Finally, feedback loops can amplify unfairness. For example, predictive policing systems trained on biased crime data may send more patrols to already over-policed neighborhoods, reinforcing the bias in future datasets. Recognizing these sources of unfairness is essential for mitigation. It highlights that fairness is not just a technical challenge, but also a social, organizational, and contextual one. This underscores that addressing unfairness requires a holistic approach spanning data governance, algorithm design, deployment oversight, and organizational accountability. A well-known case study that illustrates unfairness in AI is recruitment systems used for hiring. Several large companies experimented with AI tools to screen job applicants by analyzing resumes, test results, and online profiles. One system in particular, trained on historical hiring data, began to show a preference for male candidates. The reason? The company's workforce had historically been dominated by men, and the AI learned to treat male-associated terms, such as participation in male-dominated sports or clubs, as indicators of success. Conversely, resumes containing words like women's chess club were penalized. This resulted in discriminatory outcomes, disadvantaging female applicants. Importantly, the bias was not intentional. No one explicitly programmed the system to discriminate. However, because the training data reflected historical inequalities, the AI perpetuated them. The case underscores the importance of auditing training data and continuously monitoring algorithmic decisions. It also demonstrates the reputational and legal risks. Once the issue became public, the company had to discontinue the system and face significant criticism. The lesson here is clear. Fairness must be tested and validated throughout the AI lifecycle, especially in high-stakes contexts like recruitment. This shows how even unintended bias can cause discrimination, making proactive fairness measures essential. Ensuring fairness requires measurable indicators. Several metrics have been developed to assess whether AI systems treat groups equitably. Demographic parity requires that outcomes are distributed equally across groups, such as men and women receiving job offers at the same rate. Equal opportunity focuses on true positive rates, ensuring that qualified candidates are equally likely to be selected regardless of group membership. Equalized odds goes further by requiring both true positive and false positive rates to be similar across groups. Predictive parity ensures that predictions, such as risk scores, mean the same thing for all groups. For example, A loan approval score of 0.8 should reflect the same likelihood of repayment regardless of race. Calibration checks that probability estimates are consistent across groups. These metrics often conflict. Optimizing for one may reduce performance on another, making trade-offs inevitable. Therefore, fairness is not a one-size-fits-all concept, but requires careful alignment with organizational values, legal requirements, and stakeholder expectations. Choosing fairness metrics should involve multidisciplinary input, including technical experts, ethicists, and affected communities. This emphasizes that fairness can and must be quantified, but also that selecting the right metric depends on context, values, and regulatory requirements. Fairness in AI often involves navigating difficult trade-offs. Optimizing for accuracy may sometimes conflict with fairness goals. For example, a medical diagnostic model might achieve higher accuracy overall by prioritizing the group most represented in the data, but this comes at the expense of minority groups. Similarly, achieving demographic parity may require adjusting decision thresholds in a way that reduces efficiency. These trade-offs are not purely technical. They reflect ethical and societal choices. Which groups should be prioritized? What risks are acceptable? Should fairness be evaluated at the individual level, where each person is treated the same, or at the group level, where equity among categories is emphasized? Trade-offs also occur across time. A system that is fair today might become unfair tomorrow as populations and contexts change, requiring continuous monitoring and adjustment. Regulatory frameworks, such as the EU AI Act, expect organizations to document these trade-offs and justify their decisions. Transparency about how fairness is defined and balanced is essential for accountability and trust. This makes clear that fairness is not about achieving perfection, but about making informed, justifiable choices that balance competing objectives responsibly. Fairness begins at the stage of data collection. If the input data is incomplete, biased, or unrepresentative, no amount of algorithmic fine-tuning can fully eliminate unfairness. Data collection processes must be designed to ensure representation of diverse populations. For example, a healthcare AI trained only on data from young adults may perform poorly for older patients. Similarly, speech recognition systems trained primarily on voices with one accent may struggle with others. Inclusive data collection means seeking balance across gender, ethnicity, age, socioeconomic status, geography, and other relevant factors. It also requires transparency, documenting how data was sourced, what limitations exist, and which groups may be underrepresented. Ethical considerations also apply. Collecting sensitive attributes such as race or health status raises privacy issues, but not collecting them makes it impossible to measure fairness. Organizations must strike a balance by using privacy-preserving techniques like anonymization or federated learning. In addition, data quality checks are essential to identify errors, outliers, or skewed distributions that may distort outcomes. This highlights that fairness is not an afterthought. It starts with responsible, inclusive, and well-documented data collection practices. Without this foundation, achieving non-discrimination in AI becomes nearly impossible. Once data is collected, preprocessing techniques can be applied to improve fairness before training begins. One common method is rebalancing datasets through oversampling underrepresented groups or undersampling overrepresented ones. This helps correct imbalances, but must be done carefully to avoid distorting the dataset. Another approach is reweighting data points so that instances from minority groups carry more influence during training. Data transformation methods, such as removing or modifying sensitive attributes like gender or race, can also help. However, simply dropping these variables does not always solve the problem, since proxies, such as zip code, may still carry discriminatory signals. More advanced methods, like fair representation learning, attempt to create latent features that preserve predictive accuracy while minimizing discriminatory information. Preprocessing also includes data cleaning to remove biased labels or incorrect annotations. For example, historical arrest records may contain systemic bias. If left uncorrected, they perpetuate unfairness. Preprocessing is powerful because it addresses unfairness at the root, but it also has limits. It cannot fully eliminate contextual or deployment-related discrimination. This emphasizes that preprocessing is a key part of a fairness toolkit, but must be combined with in-model and post-processing interventions for comprehensive impact. In-model fairness techniques modify the training process itself to prevent discriminatory outcomes. One approach is regularization, where fairness constraints are added to the optimization objective. For instance, the model might be penalized if prediction outcomes differ significantly across groups. Another method is adversarial debiasing, where a secondary model tries to predict sensitive attributes from the main model's outputs. The main model is then trained to minimize both prediction error and the adversary's ability to detect sensitive information. This encourages fairness by reducing group-specific signals. Fair representation learning is another technique, ensuring that the model learns internal features that are predictive but not correlated with sensitive attributes. Some algorithms are designed with fairness inherently built in, such as decision trees that enforce parity constraints. Importantly, in-model approaches often involve trade-offs between fairness and accuracy, requiring careful parameter tuning and validation. They also require technical expertise, making them less accessible to non-specialists. Nevertheless, they are valuable because they embed fairness into the model itself rather than relying solely on external corrections. This demonstrates that fairness can be engineered into the training process, making it part of the model's DNA rather than a post hoc adjustment. Post-processing techniques are applied after a model has been trained, focusing on adjusting its outputs to achieve fairer outcomes. One common method is threshold adjustment, where different decision thresholds are set for different groups to equalize outcomes. For example, in a loan approval model, the cutoff score for approval may be adjusted slightly for underrepresented groups to ensure equal opportunity. Another method is calibration, where probability scores are adjusted so that they reflect the same meaning across groups. Post-processing can also involve output constraints, where the distribution of predictions is forced to meet fairness criteria like demographic parity. While these techniques can quickly mitigate bias, they raise important questions. Should outcomes be manipulated after training, and how transparent should these adjustments be? Critics argue that post-processing may obscure underlying problems rather than addressing their root causes. However, in regulated industries or urgent contexts, post-processing can be a pragmatic solution when retraining the model is not feasible. Documentation is critical. Organizations must record why and how adjustments were made and be transparent with stakeholders about the implications. This highlights that post-processing is a valuable but limited tool. It can correct unfair outcomes in the short term, but it is not a substitute for fair data collection and model design. Fairness in AI is not static. A model that appears fair at launch may drift toward unfairness over time as populations, data distributions, or usage contexts change. Continuous monitoring is therefore essential. This involves tracking performance metrics across different demographic groups, conducting periodic fairness audits, and setting up automated alerts when disparities exceed acceptable thresholds. Monitoring should cover both technical outputs and real-world impacts. For instance, a credit scoring system may meet statistical fairness metrics but still result in unequal loan access for certain communities due to structural barriers. Organizations should also involve stakeholders, including affected groups, in reviewing monitoring results to ensure fairness is interpreted in socially meaningful ways. Monitoring must be documented, with clear accountability for who reviews results and takes corrective action. Regulatory frameworks, such as ISO 42001, emphasize ongoing evaluation and continuous improvement, not one-time compliance. Effective monitoring may even require external audits to ensure impartiality. This emphasizes that fairness is not a one-off achievement, but a continuous commitment. By embedding fairness monitoring into governance structures, organizations can adapt to change and maintain trust over the long term. Even the most advanced fairness techniques cannot replace human judgment. Human oversight remains critical for ensuring AI systems operate fairly and avoid discriminatory outcomes. Oversight begins with diverse and inclusive development teams that can identify potential biases others may overlook. It also requires decision makers to critically examine algorithmic recommendations rather than accepting them blindly. For example, in hiring, recruiters should review AI-generated shortlists to confirm they do not disadvantage qualified candidates from underrepresented groups. Oversight should be structured, with clear roles and responsibilities defined in governance policies. ISO 42001 and the NIST AI Risk Management Framework highlight human oversight as a safeguard against unfair outcomes, requiring that humans remain in the loop or on the loop, depending on the system's risk level. Transparency tools, such as explainable AI dashboards, can empower human reviewers to spot patterns of unfairness. Importantly, oversight is not about occasional checks, but about embedding fairness review into organizational processes. This includes escalation procedures when unfairness is detected and accountability mechanisms to ensure corrective action is taken. This emphasizes that fairness requires a human lens. People must remain actively involved in verifying, questioning, and correcting AI decisions to safeguard non-discrimination. Fairness in AI cannot be achieved solely by developers or regulators. It requires stakeholder involvement throughout the AI lifecycle. Stakeholders include not only system designers and users, but also those directly affected by AI outcomes. For example, if a city deploys predictive policing algorithms, communities most impacted should be consulted about risks, safeguards, and oversight mechanisms. Involving stakeholders provides two key benefits. First, it improves fairness by identifying potential issues early. People with lived experience often recognize biases that technical teams may overlook. Second, it builds legitimacy and trust, showing that AI systems are developed in consultation with the people they affect. Stakeholder engagement can take many forms: focus groups, public consultations, advisory panels, or co-design workshops. Organizations should document these engagements to demonstrate accountability. The OECD AI Principles and UNESCO AI Ethics Recommendation both highlight the importance of inclusivity and stakeholder participation. However, involvement must be genuine, not symbolic. Token consultations that do not influence outcomes risk further eroding trust. This stresses that fairness is a shared responsibility, requiring dialogue and collaboration with stakeholders to ensure AI systems reflect social values and avoid discrimination. High-risk AI systems, those that directly impact fundamental rights, livelihoods, or safety, require heightened fairness safeguards. Examples include systems used in healthcare diagnostics, recruitment, credit scoring, and law enforcement. Because these applications influence access to essential services and opportunities, unfairness can cause severe harm. The EU AI Act explicitly classifies such systems as high risk and mandates rigorous fairness, transparency, and accountability measures. ISO 42001 also requires organizations to assess fairness risks and implement proportionate controls based on system impact. In high-risk contexts, fairness cannot be optional or secondary. It must be central to system design and governance. Techniques like diverse data collection, fairness metrics, and independent audits are mandatory rather than recommended. Moreover, organizations must provide detailed documentation showing how fairness has been considered and achieved. This may include fairness impact assessments, stakeholder consultations, and continuous monitoring reports. The goal is not only to reduce discriminatory outcomes, but also to provide evidence of compliance to regulators and affected communities. This underlines that fairness is most critical where stakes are highest, and organizations must treat it as a core compliance requirement. Transparency and fairness are deeply interconnected. Without transparency, it is nearly impossible to detect, measure, or address unfairness. Transparency means providing clear and accessible information about how AI systems work, what data they use, and how decisions are made. For example, if a loan approval system rejects an applicant, the organization should be able to explain the key factors behind the decision. Transparency supports fairness in two ways. First, it enables accountability. Regulators, auditors, and affected individuals can scrutinize outcomes to ensure non-discrimination. Second, it empowers stakeholders by giving them the knowledge to challenge unfair outcomes. Transparency does not require exposing proprietary algorithms, but does require meaningful disclosure. Techniques like explainable AI, model cards, and data sheets for datasets help organizations communicate system behavior. Regulatory frameworks, including the EU AI Act and ISO 42001, mandate transparency measures precisely because they enable fairness. Without visibility into how models function, fairness risks remain hidden and unaddressed. This highlights that fairness cannot exist in a black box. Only through transparency can organizations verify, demonstrate, and maintain non-discrimination in AI systems. Accountability mechanisms ensure that fairness commitments are not just promises, but operational realities. Accountability begins with assigning clear roles and responsibilities for fairness within the organization. This includes designating fairness officers, ethics committees, or AI governance boards to oversee compliance. Documentation is another critical mechanism. Organizations should record fairness assessments, bias testing results, and mitigation strategies, creating an audit trail. Regular reporting, internally and externally, demonstrates ongoing commitment and allows for public scrutiny. External audits provide additional assurance, offering independent evaluation of fairness practices. Legal liability frameworks also serve as accountability mechanisms. If an AI system causes discriminatory harm, organizations must be prepared to accept responsibility. Importantly, accountability is not about blame, but about ensuring continuous improvement. Mechanisms such as feedback loops, corrective action plans, and performance incentives tied to fairness outcomes help drive progress. Standards like ISO 42001 emphasize accountability as a management system requirement, embedding it into governance structures. This reinforces that fairness requires not only technical tools, but also organizational accountability structures that ensure sustained, verifiable, and enforceable commitment to non-discrimination. A fairness impact assessment is a structured process to evaluate how an AI system may create or exacerbate unfair outcomes. Similar to privacy impact assessments, FIAs systematically identify risks, evaluate potential harm, and propose mitigation strategies. They typically include questions such as, who are the affected groups? How representative is the data? What fairness metrics apply to this context? What trade-offs are being made? FIAs encourage organizations to move fairness from abstract principles to concrete, documented practice. For example, before deploying a credit scoring system, an FIA might reveal that the training data underrepresents rural applicants, prompting corrective actions. Regulators are beginning to require such assessments. The EU AI Act mandates risk management processes that include fairness considerations, and ISO 42001 calls for documented assessments across AI lifecycle stages. Importantly, FIAs should not be one-off exercises. They must be updated as systems evolve and new risks emerge. Stakeholder consultation is also critical, ensuring that the voices of affected groups inform the analysis. This underscores that FIAs provide both a compliance tool and an ethical checkpoint, helping organizations proactively identify and address discrimination risks. Auditing AI systems is a vital step to ensure fairness commitments are met in practice. An audit involves systematically reviewing an AI system's design, data, models, and outcomes against defined fairness criteria. Internal audits allow organizations to self-assess compliance, while external audits provide independent assurance and credibility. Fairness audits typically include testing outputs across demographic groups, reviewing data sourcing practices, and verifying the application of fairness metrics. Auditors also evaluate governance processes, such as whether fairness impact assessments were conducted and whether mitigation measures were implemented effectively. Some industries are beginning to formalize fairness audits. For instance, financial regulators in several jurisdictions require lenders to demonstrate that automated decision-making tools comply with anti-discrimination laws. Audits also align with ISO 42001's requirement for evidence-based verification of fairness practices. Challenges remain. Audits require access to sensitive data, technical expertise, and standardized methodologies, which are still developing. Nevertheless, they are critical for accountability, transparency, and trust. This emphasizes that fairness cannot be assumed. It must be verified, documented, and independently confirmed through rigorous audits. Fairness in AI is a global concern, but interpretations and approaches vary across regions. In the European Union, fairness is embedded in fundamental rights and operationalized through the EU AI Act, which mandates fairness safeguards for high-risk AI. In the United States, fairness is often framed through anti-discrimination law and sector-specific regulations, such as those governing credit or employment. Canada's proposed Artificial Intelligence and Data Act, IDA, requires proactive measures to mitigate biased outcomes. In Asia, countries like Singapore promote fairness through voluntary frameworks emphasizing trust and transparency, while China integrates fairness requirements into its broader AI governance rules. International organizations also play a role. The OECD AI Principles and UNESCO AI Ethics Recommendation both emphasize fairness and inclusivity as global standards. Despite differences, a common theme emerges. Fairness is increasingly seen as a non-negotiable requirement for trustworthy AI. Organizations operating internationally must adapt to diverse legal and cultural expectations, balancing compliance with global consistency. This highlights that fairness is not just a local issue, but a global responsibility, requiring organizations to stay informed about evolving regulatory and ethical landscapes. Fairness in AI cannot be achieved by technical fixes alone. It must be embedded in organizational culture. A culture that prioritizes fairness encourages employees to raise concerns, challenge biased practices, and seek inclusive solutions. Leadership plays a critical role by setting expectations, allocating resources, and demonstrating commitment through policies and actions. Training programs help staff understand fairness concepts, identify bias, and apply mitigation techniques. Diversity in teams also contributes significantly, as varied perspectives make it easier to spot potential unfairness. Organizations should integrate fairness into their values, performance indicators, and incentive structures. For example, fairness metrics could be part of annual performance reviews for teams working on AI projects. Whistleblower protections and open communication channels ensure employees feel safe reporting fairness concerns. ISO 42001 emphasizes continuous improvement, which requires cultural support to sustain fairness over time. This reinforces that fairness is not just a compliance exercise, it is a mindset. Building an organizational culture of fairness ensures that non-discrimination is consistently prioritized across projects, decisions, and strategies. The field of AI fairness is rapidly evolving, with new research shaping both technical methods and policy debates. Scholars are developing more sophisticated fairness metrics that capture complex realities, such as intersectionality, where individuals belong to multiple disadvantaged groups. Technical advances include methods for fairness in reinforcement learning, fairness-aware federated learning, and causal approaches that identify root causes of unfairness rather than correlations. Researchers are also exploring fairness beyond traditional protected attributes, considering socioeconomic status, geography, and even environmental impacts. On the policy side, debates continue about whether fairness should prioritize equality of outcomes, equality of opportunities, or broader social justice goals. Industry consortia and academic collaborations are producing open-source fairness toolkits, making practical adoption easier. At the same time, critical perspectives caution against over-reliance on technical fixes, urging deeper reflection on the social and political dimensions of AI. For organizations, staying updated on emerging research is essential to remain compliant, competitive, and ethically aligned. This emphasizes that fairness in AI is not static, but an evolving discipline. Practitioners must continually adapt by integrating new insights, tools, and frameworks into their AI governance practices. Despite widespread recognition of its importance, implementing fairness in AI remains challenging. One key difficulty is the lack of consensus on what fairness means in practice. Different fairness metrics can produce conflicting results, forcing organizations to make trade-offs without clear guidance. Another challenge is data limitations. Sensitive attributes such as race or gender are often missing, incomplete, or legally restricted, making fairness measurement difficult. Technical complexity is also a barrier. Fairness methods require advanced expertise and can be computationally costly. Beyond technical hurdles, organizational barriers exist. Some companies may prioritize speed to market or profitability over fairness, while others may lack leadership commitment or resources to invest in fairness safeguards. Regulatory uncertainty adds another layer of complexity as global requirements vary and continue to evolve. Finally, fairness efforts may face social resistance if stakeholders perceive interventions as unfair to other groups or as manipulations of outcomes. These challenges highlight that fairness is not a simple technical fix, but a multidimensional effort requiring legal, social, organizational, and technical alignment. This stresses the importance of recognizing and addressing these obstacles proactively to make fairness both achievable and sustainable. The future of fairness in AI is likely to be shaped by both technological innovation and regulatory evolution. Technologically, advances in explainable AI, causal inference, and federated learning are creating new opportunities to build fairer systems without compromising privacy or accuracy. Intersectional fairness, ensuring fairness across multiple overlapping identities, is becoming a research priority. On the regulatory side, comprehensive frameworks like the EU AI Act will set stricter fairness obligations, influencing global best practices. Industry trends also point toward greater adoption of fairness toolkits and standardized auditing methodologies, making fairness more operationally feasible. Another promising direction is the integration of fairness into AI supply chains. As organizations increasingly rely on third-party AI tools, vendors will face growing pressure to provide assurances of fairness through certifications and transparency reports. Education and workforce development will also play a crucial role, equipping AI professionals with the skills to identify, measure, and mitigate unfairness. Ultimately, the future direction is toward mainstreaming fairness, making it a standard part of AI governance rather than a specialized concern. This emphasizes that fairness will evolve from being an emerging challenge to a mature discipline, shaping the trustworthiness and societal impact of AI for decades to come. As we conclude, let's recap the central message. Fairness and non-discrimination are not optional features of AI systems, but essential principles that ensure technology serves society responsibly. We began by defining fairness and exploring the many ways bias can arise, from data to algorithms to deployment contexts. We examined techniques for promoting fairness, pre-processing, in-model adjustments, and post-processing, while stressing the need for continuous monitoring and human oversight. We also highlighted the legal, ethical, and organizational foundations of fairness, showing how frameworks like ISO 42001, the NIST Artificial Intelligence Risk Management Framework, and the European Union Artificial Intelligence Act embed fairness into governance structures. Through case studies, metrics, and real-world applications, we saw how unfairness can harm individuals, erode trust, and expose organizations to significant risks. At the same time, fairness offers strategic advantages: stronger reputation, regulatory compliance, and better alignment with societal values. Challenges remain, including data limitations, technical trade-offs, and organizational barriers, but the trajectory is clear. Fairness is becoming a mature discipline supported by emerging research, regulatory developments, and industry standards. The key takeaway is that fairness must be embedded across the AI lifecycle, from data collection to deployment and monitoring, and supported by culture, accountability, and stakeholder involvement. By committing to fairness, organizations can ensure their AI systems not only avoid discrimination, but actively contribute to a more inclusive and equitable society. This knowledge provides you with a strong foundation to aid you in the future, whether you apply it in your current role, pursue further study, or contribute to shaping responsible AI in your organization. By staying informed and engaged, you will play a vital role in ensuring AI develops in ways that are safe, ethical, and beneficial for society. Thank you for your time and your commitment to this learning journey. We encourage you to keep exploring and keep building toward a future where artificial intelligence serves the needs of humanity responsibly.